So we are on to our very last example with proofs by mathematical induction. This one's slightly different in that we aren't trying to prove a sum or an equation, but rather we are trying to prove divisibility. We want to prove that 6 to the power of n minus 1 will always be divisible by 5. Because we're going to prove this by mathematical induction, I did include our 3 steps again over on the upper right-hand corner of the screen. We need to do the base case, the induction hypothesis, and then the actual induction. Let's go ahead. First, we need to show that our base case statement is true. 6 to the first power is 6, minus 1 equals 5. And 5 divided by 5 equals 1. So 5 is divisible by 5 because we got an integer as our answer. Now we can move on to our induction hypothesis. This is where we want to assume that 6 to the power of k minus 1 is divisible by 5. But ultimately, what does that mean in terms of algebra? Like, what would I need to actually show if something's divisible by 5? Well, just like in our base case, we know that when we plug in a number into the exponent for k, and then we subtract 1, we must get a number that is divisible by 5. Therefore, 5 times some integer should equal 6 to the power of k minus 1. That means that the right-hand side of this equation, when we divide by 5, will always be an integer, which means that it's ultimately divisible by 5. So let's go ahead and move on to the actual proof by induction. This is where we want to be able to show that 6 to the power of k plus 1 minus 1 also equals 5x because we want it to be divisible by 5, where x is an integer. Well, by exponential rules, we can actually write the 6 to the power of k plus 1 as 6 to the power of k times 6. Remember, if the bases are the same, you can add the exponents, which means ultimately you can decompose this into 6 to the power of k and 6. So I'm going to do that to start out with. But look at this. We have 6 to the power of k here, and we had a 6 to the power of k in our induction hypothesis. In fact, rearranging our induction hypothesis statement, we know that 6 to the power of k will equal 5 times x, where x is an integer, plus 1. This means we can go ahead and substitute this in for this 6 to the power of k. I'm going to go ahead and do that substitution here. So I now have 5x plus 1 times 6 minus 1. I'm going to go ahead and distribute the 6 in. When I do that, I get 30x plus 5. How is this helping me? Let's go back and remind ourselves of what our goal is. We're trying to show that the left-hand side that we started with is divisible by 5, or is 5 times x, where x is an integer. Keeping in mind it can be 5 times any integer. What do you notice about 30 and 5? That's right. They both have 5 as a factor, so we can actually factor out a 5. After factoring out the 5, I get 5 times 6x plus 1. Now, because the integers are closed under multiplication and addition, I know that if x is some integer, even when I multiply it by 6 and add 1, it's still going to be an integer. That means that this 6x plus 1 is an integer, and 5 times any integer means that our initial statement, our 6 to the power of k plus 1 minus 1, will be divisible by 5. So lastly, we just need to include our concluding statement. 6 to the power of n minus 1 will always give us a number that is divisible by 5, which we just proved by the principle of mathematical induction. Nice work.